All right, let's dive into two of the absolute workhorses of digital electronics. Now, on the surface, they just look like simple switches, but trust me, there's a whole lot more going on under the hood. They're hiding some pretty incredible power. So let's crack open this case and really see what makes them tick.
I mean, have you ever really stopped to think about this? Every single time you click your mouse, press a key, or even just see a pixel change on your screen, a decision is being made. A choice, right? A choice between millions of different possibilities, all happening in a blink of an eye. So, how on earth does a computer do that so fast?
Well, the answer is surprisingly elegant, actually. It all comes down to a component that's basically like a railroad switch, but for data. Its job is just to direct all that digital traffic down one single specific path. And right at the heart of this whole process is a little device we call a data selector. And that, right there, brings us to our first component, the multiplexer, or, as everyone calls it, the MUX. Its job is crystal clear. You give it a whole bunch of different input lines, and its entire purpose is to pick exactly one of them and shoot it down a single output line. You can think of it as the ultimate many-to-one data funnel.
Okay, so let's get into our first section here, the data selector. Before we get to all the cool hidden tricks, we really need to nail down its main job. So how does it actually make that choice? How does it know which data to send through?
You know, the whole process is actually pretty clever and simple. So let's picture a MUX with 4 inputs. Think of it like 4 doors, and there's data waiting behind each one. Now, the MUX also has these 2 special control inputs. We call them select lines, and these lines get a binary code, right? Let's say it gets the code 01. That code is like an address. It's basically telling the MUX, hey, open door number 2. And boom, just like that, the data from that specific door gets sent out the single exit, while all the other data just waits its turn.
Okay, so that's getting data in, but you know how it goes. For every action, there's an opposite reaction, right? Well, it's kind of the same in digital logic. The opposite of funneling all this data into one spot is, you guessed it, spreading it all back out. And that brings us to the MUX's counterpart, in our next section, the data distributor.
So let me introduce you to the demultiplexer, or DMUX. And yeah, it does the exact opposite of what we just saw. It takes one single input stream of data and, using those same kinds of select lines as before, it routes that data to one of many possible outputs. It's a one-to-many device, the perfect opposite.
So let's just nail this down. The key difference is super simple. A MUX selects, a DMUX distributes. The MUX is many-to-one, the DMUX is one-to-many. They're literally 2 sides of the exact same data routing coin.
But, and this is where things get really interesting, if you think that's all these little guys can do, just route data around, oh, you are in for a surprise. It's time to dive into our next section, the secret life of switches. I mean, selecting and distributing data, that's useful for sure. But what if I told you that this simple switch could do more? What if it could actually do math? Seriously, what if it could add numbers?
Okay, check this out, because this is where the MUX reveals its secret identity as a tiny calculator. Let's say you want to add 2 bits, we'll call them A and B, plus a carry-in bit. You can actually do this with a 4x1 MUX. You just wire up A and B to the select lines. But here's the trick, the secret sauce, the data inputs. You don't feed them normal data. Instead, you wire them up to the carry-in bit, or its inverse, in a very specific pattern. So now, when the MUX uses A and B to select an input, it's actually selecting the correct logical outcome. And voila! The output is the correct sum. It's not using logic gates. It's doing addition just by selecting.
And this is just a brilliant example of the practical advantage here. As the folks at Nesso Academy put it, by using a single IC, you do not require different gates, you do not require wires, and it's very simple. It's just cleaner, way more efficient, and honestly, kind of beautiful in its elegance.
And don't worry, the DMUX isn't getting left out of the party. It has its own secret talents too. With some of that same clever wiring, you can make a 1-to-8 DMUX work as a full subtractor. But even cooler, if you just permanently set its data input to 1, it stops being a DMUX entirely and magically transforms into a completely different component called a decoder. I mean, that level of versatility is exactly what makes these things so darn powerful.
So all this versatility leads us straight to another one of their key jobs. I mean, what do you do when you need a really big, complex circuit? Well, you don't always start from scratch. A lot of the time, you just use these simple components like Lego bricks, which brings us to our next section, building bigger with less. All right, let's say you're in a situation where you need an 8-input MUX, but all you've got is a bunch of tiny 2-input MUXes.
No problem at all. There's actually a really simple division method you can use. You just take your target, 8, and divide by what you have, 2. That's 4. Okay, then you take 4, divide by 2, that's 2. Take 2, divide by 2, that's 1. Now just add up the results, 4 plus 2 plus 1, and you know you need exactly 7 of your little muxes, all arranged in stages, to build the big one. Pretty neat, huh?
But what happens when the math doesn't play nice? What if you need to build that same 8-input mux, but this time you're using 4-input muxes? Okay, so you do the math. 8 divided by 4, that's 2. But now you're stuck. You try to divide 2 by 4, and you get a fraction. You get 0.5. The whole method just breaks down. You can't exactly use half a mux, right? So now what do?
Well, this is where some really clever engineering comes into play. The solution lies in a special pin that most muxes have, called the enable pin. And it does exactly what it sounds like. It turns the whole mux on or off. So here's the trick. You take your two 4x1 muxes, you use the most important select line, let's call it S2, not to select data, but to act as a master switch. You connect it to the enable pin on one mux and an inverted version of it to the other. So now when S2 is 0, the first mux is on and the second is off. When S2 is 1, the opposite happens. It's a brilliant little workaround that gives you the full 8-input functionality you needed.
So when you start to put all these different pieces together, you realize pretty quickly that these are not just simple switches. They are so much more. Which brings us to our final takeaway, the digital Swiss Army knife.
I mean, think about all the tools we just unpacked. Yeah, they're a data selector, a classic many-to-one, and they're a data distributor, a one-to-many. But they're also a logic function implementer, a tiny calculator. And on top of all that, they're a modular circuit building block. They really, truly are the Swiss Army knives of the digital world.
And I think that's really the big takeaway here. In a world that is just getting more and more complex, the mux and demux are this perfect testament to the power of simple, elegant design. They prove that sometimes the most powerful and versatile tools are the ones that have been hiding in plain sight all along.
And it really makes you wonder, doesn't it? What other simple, everyday components are out there, just hiding these incredible, powerful secrets? What else are we taking for granted that's secretly capable of so much more?